let's start with gradient descent in convolutional neural networks. And I want to start with a little bit of a warning. So there's a lot of math coming up. Don't be afraid. The slides have been designed such that they're self-contained. So I really encourage you, after today, go home, relax, go through those slides one by one. If there are some details that you don't get right away, it's kind of normal, especially if this is new for you, especially if you haven't done math in a while. The purpose of this is really that you're here to learn. You're here to see these derivations. It's important to understand them at least once in your life, such that when you're using convolutional neural networks, it's a lot easier to have an intuition as to what might be going wrong when things don't end up working as you expect. Okay, but again, I really encourage you to sort of try and follow what's happening, but go home and really go over these slides in depth on your own free time. Okay, so let's start with a bit of a recall as to what gradient descent is. So yesterday, Gaetan introduced the gradient descent algorithm and backpropagation. And so there are multiple steps involved into performing gradient descent, or stochastic gradient descent. So the first step is to compute the forward pass. So we have an input, we have our neural network, and we compute the output to our network. That's called the forward pass. We then want to compute the derivative of the loss through a backward pass. Finally, we want to update all the tunable parameters of the network. Okay, so these are kind of the three main points of the recipe to doing gradient descent. So let's start by setting up our problem. So we're going to consider a very simple case. So we have a CNN. Our input x is a 3 by 3, a matrix, which we have over here. And the indices denote the different elements in the matrix. So x11 is a number, a floating point number. And our kernel, w, is a 2 by 2. So again, we have the different indices representing our kernel. We're using no padding. We're using a stride of 1. And again, just a little reminder, this is the convolution operation. So let's start building our graph, our computational graph. Right? So this is how we can sort of represent this in terms of a graph. So we have our inputs x, we have our kernel w, and we're performing some kind of convolution, and we're going to get an output here. So let's start by computing the forward pass. So by now, you've seen how to compute convolutions in a neural network. So let's view this a bit more explicitly. So we take our kernel, and we place it over in our input such that it's in a valid position, right? So the valid convolution. And so what this means now, we do our element-wise multiplication. So we have x11, we multiply that by w11, it gives us this term here. We then perform the same thing for x12 and w12, x21, w21, and x22, w22. And we sum all of these together. And that gives us our first output in our matrix. We continue doing this, so we slide our kernel again, and again, and again. And again, this is the representation. So if you were to crunch some numbers, you would get some numbers coming out of this. But now we're generalizing this to any sort of number that we can get. And for notation purposes, because this is just becoming a little cumbersome, we're going to note this as y11, y12, y21, y22, which is the output of our network. So now we can fill out our graph such that we have our output of our network over here. So up until now, this should have just been a bit of an update based on what we saw in the first lecture. So one thing that I want you to notice is that this is equivalent to performing the following matrix multiplication. So we take our input x, and we unroll it from left to right, top to bottom. So here we take our input x, and all we do is, instead of having a matrix, we now represent it as a vector by using this unrolling technique. We then construct our matrix w here for our weights based on the stride, the padding, all the different parameters that we've defined. And it turns out that if we do the matrix multiplication x times w, we get the exact same input that we computed before. Now, this is really useful because now we're able to define our convolution as a matrix operation instead of having it be this sort of procedural technique where we go one by one with these squares. Now we need to define our loss function. So what is the loss function we saw yesterday? It's how we evaluate the error between the output we expect from our network, here that I'm denoting y hat, and the output we computed y. So our network gives us a prediction y, and we want to compare it with some kind of ground truth, which we know is the real reality of what these values should be. And these are the values that we know to be the truth, and we provide them to the network. So in this example, we're going to use a specific case of a loss function called the L2 norm. So the L2 norm computes the Euclidean distance between 2 points and also adds a factor of 1/2 in front of it. So why do we have this factor of 1/2 in front of it? Because it turns out that when we calculate the derivative, so again, going back to calculus courses, if we take the derivative, the 2 here factors out our 1/2, and our derivative of the error with respect to our outputs turns out to be as simple as computing the difference between the output we predicted and the output we expect. So that's a very cheap operation. We just have to do a subtraction. So that's why this loss is really useful to use. And we could have used other losses, but for this specific example, we're using the L squared norm. So let's continue building our graph. We had our inputs. We convolved them with our kernel. We have our outputs. Now we add our loss. So here we have our loss term. And to compute our loss, we use our ground truth. And then we can compute our error. So now this is what our whole graph operation kind of looks like. So we've deconstructed our whole network. And again, we have our inputs. We have our kernels. We perform our convolution. And we compute the loss to get our error. So remember that what we're trying to do is gradient descent. So what we want to do is we want to calculate the update rule for all of the parameters that we can tune in our network. Remember that in the convolution case, what we're learning are the parameters for our kernels. So we initialize them at random at first, and we want our network to learn what the best kernels are to solve our task. So we want to first figure out these parameters right here. Right, we can then compute the update rule, which you saw yesterday, based on gradient descent. So the wij will be wij minus the learning rate times the derivative of the error with respect to the parameter ij. So in this case, right, the tunable parameters that we're going to focus on right now are in yellow. So we want to figure out in which direction should we step to update these parameters to optimize our function. So what we need to really compute is the derivative of the error with respect to all wij's, this term right here.